Okay, so let us see. I hope you remember about fractals, right? What are fractals? Fractals are geometrical objects which have self-similar behavior at infinite scales, right? So an example we saw, I hope you remember those examples, like these veins, right? So they have self-similar structures. Like as whenever you zoom in, the similar kind of structures you see again and again. Okay, but there is a limit. I mean, after a lot of zooming, you will start to see atoms and molecules, not through our eyes, but through microscopes and all, right? Fine. You can see another example like snowflakes. Also lightning, right? Lightning is a very good example of a fractal. Okay. So how this, can you describe the geometry of lightning? So it's by fractals. You cannot explain this geometry of lightning by normal geometry which you have learnt in school days, right? Even the coastlines. So it is not like a smooth line. So this is what I have drawn. Can you approximate these boundaries of this iceberg as smooth curves? So see, if I am even drawing with pen, it is a smooth curve. It is a smooth curve, right? But actually, do you think actually that actually the boundary is smooth? No, it is comprised of very tiny and lot of sharp points, right? And this is how you make fractals. So nature follows the geometry of fractals. What's the shape of the clouds? We don't know. Shape of the clouds are fractals. Okay, we cannot draw shape of clouds like this when we were drawing in school days. Okay, so therefore this is not only macroscopic but also microscopic. The fractals are also present at microscopic levels. You can see these are the examples, like experimental examples of microscopes. I think it is transmission electron microscope. I hope you remember the transmission electron microscope if you have done your undergrad in physics or chemistry, or maybe biology also. Like these are the pictures you see. Okay, so you can see these branchings. If you see these branchings, the more and more I zoom, you can see the self-similar branching structure like in trees are present. Okay, so this is one of the ideas, right? Fine. And then we saw that how in video games also fractals are present. How video games are able to replicate the geometry of the trees or geometry of any real life object in such nicely, in a very nice way, that you feel that they are real, right? You get a perception that they are real. So how they are creating the geometry using fractals. But how they are computing fractals? Of course, by writing codes. So there are ways. So we'll see them in this class, like using L systems. Like this is an algorithmic way of creating fractals, right? You tell it's like logo. How many of you have gone through class logo in school days? Logo? Hmm? Yes. I mean, you say forward. You say forward, forward 60, angle 60, right? Turn 30 degrees. Do you remember logo? Yeah. So actually this I had learned in my fourth class, logo. Okay. Logo. So we were taught, like, if you want to go simple like this, so they will give you a structure, like how you will go like this in a computer program, right? So you will say start from 0, 0, go rightwards towards 30 meters or whatever, 30 units, then turn up. Okay, then go right, turn up, go right, like that. So there are more complicated figures you can draw also like this. So this was we learned in ICSE fourth class. So these are just logo commands, right? Anyway, so similarly, similar commands you can give during your fractal construction. So these are known as L system. You can see these are L systems. So through L systems, you can create structures like this. Okay, so same we will see, just very brief you will see. We will not see much detail, but through L systems, you can actually create gaming structures, gaming fractals, fractals present in your games. Okay. So that's one of the nice cool structures. Okay, and we saw that you actually see these in trees and broccoli also. So a small part of broccoli you take, a small part of broccoli, and you zoom this broccoli again, so it will look like the bigger broccoli, right? It will look like the bigger broccoli. So that's how it is self-similar. Okay, and scientists have already found the dimension of this broccoli, fractal dimension of this broccoli, and it is not three-dimension. You might think this is a three-dimensional object, but any object which is rough, is having a fractal dimension. I mean fractional dimension. The dimension will lie in between 2 and 3, like 2.35, dimension of 2.35. Okay, so anything you see which is rough, do you think any surface, any object you pick, like this table here, do you think it is smooth? It is smooth to your hands, okay, but do you think it is actually smooth? It is not. The more and more you will see this tiny, this is a table. So if you zoom in into this, you will see like there are small like layers like this. Okay. Because the wood is finally polished, but there is always an error how you polish. You cannot achieve highest amount of accuracy. So there will always be an error. So it is not polished 100%, right? Maybe 99.8 or 9, but still 0.1 is not polished. Anyway, so these are the ideas. Okay, now let me start with the concept of dimensions. Okay, let us start with the concept of dimension of a fractal. Okay, how to compute dimension of a fractal. So that's our topic today. So okay, so let us start with this example. I mean, we ask this simple question. So I will give you a structure and then I will ask you how much it fits. Okay, we'll start with simple thing, like this is just a unit length, the line segment. It's a line segment of unit length. I am asking that this is another line segment which is, I mean, 3 times or 4 times the length. Okay, this is 4 units. This is 1 unit. This is 4 units. So my question is, how many copies of this small unit will fit inside this big unit? Hmm? How many? 4 units. 4 units of this will fit inside this, right? Okay. Now let us ask another question, like maybe let me put this in a different way. Then we can do this experimentation. Like we will do a column of shape and then we will say magnification factor. Okay, magnification factor, and we will ask number of small copies in big copy. Okay, okay. What do I mean by that? So what I mean is, like, suppose you have this unit length and suppose this size is 3. Let me make it more simple. So I will ask, like, what is the shape of this line, right? The shape of this is a line. What is the magnification factor? I mean, how much magnification you have to do for this unit length so as to cover this length? 3 times. You have to magnify it 3 times, right? Understood? You have to magnify this. You have to magnify this 3 times, to overlap with this line, right? So the magnification factor is 3. Okay. Now, how many number of small copies you can fit inside the big copy? This is the small copy. This is the big copy. So how many? 3. 3. How many small copies you can fit inside this? I have made it 3 units now. So how many small copies you can fit? You can fit like this: 1 unit, then another 1 unit, right? Then another 1 unit, right? 1, 1, 1. 1, 1, 1. Agree? Fine? Or any issues? Because we will increase our idea. Okay, now. So number of small copies in big copies is equal to 3, right? Now let us take a square. Let us take a square. Okay. If you take a square like this, okay, if you take a square and I ask you like, maybe if you fit inside this square, Okay, so this is the big copy. This is a small copy, right? So it's 1, 1, and these are all like maybe 1, 1, 1, 1, 1, 1. Okay. So my question is again for the square, how you can go from this, how much magnification you have to do for this small box so that it can fit inside this big box? How much magnification you have to do? So what you have to do? You have to increase this line segment 3 times and increase the another line segment 3 times so that this can be covered and the horizontal thing can be covered. Then only you can cover the whole square, right? So how much you have to magnify? No, 3 times. Hmm? No, if you see carefully, I mean, don't separate it into dimensions, x and y. You think how many, like if you just scale it, just zoom it or transform it 3 times, okay, you can make it because each dimension you are transforming into 3 times, right? Okay, okay. So 3. So how many small copies you can fit inside the big copy? 9. Because 9 times 9 small copies you can fit here in each. So 9, right? Okay. Let us take a cube. Let us take a cube. Okay. Still what is it? Let us take a cube. So cube of unit length. Cube of unit length. Now I'm asking you the question like maybe like this one. Okay. Okay. I mean, yeah, not that much of a good one, but yes, you can understand. So how many times you have to stretch it? You have to stretch it on this side also, on this side also, on this side also. So magnification you have to do 3 times again. But how many copies will fit inside this? Yes, 27. Right? Agree? Okay. Now can you see some relation happening here? What is the dimension of a line? Dimension of a line is just one dimension. What is the dimension of a square? Two dimension. Dimension of a cube? Three. Can you see some relation happening here? How we can get the dimension using the two columns? Hmm? Can we write like this? Number of small copies in big copy is equal to magnification factor to the power of something. Yes. And that is the dimension. Okay. That is the dimension. So can you see for a square, for the line, maybe number of small copy is 3. Magnification factor is 3 to the power d. So what is d? 1. That is the line dimension. For a square, number of small copies is 9. Magnification factor is still 3. 3 to the power d. So implies dimension is 2. Right? For the cube, number of small copies as you told 27. Right? Is equal to magnification factor which is still 3 to the power d. Implies d equals to 3. So these matches our intuition also. This matches our intuition also, right? So I hope you are clear. Like it is clear to you that from this we can see how line is one dimension, how square is two dimension, how cube is three dimension. Now why this is essential? Why at all we are doing this? I mean, why at all we are doing this? We are doing this to we will apply the same idea to compute dimension of a fractal. We'll apply the same idea to compute the dimension of a fractal. Okay. Fine. Okay. I hope you are now comfortable with the idea of number of small copies and the magnification factor. Now let us take a fractal and apply it. Okay, let us take a fractal. Okay. Okay, now my question is, can we compute the dimension of this fractal? Can we compute the dimension of this fractal? That's my idea. So you can see the dimension of this fractal, how this fractal is constructed. Just look into this figure. I will give you 1 minute how this is constructed. Then I will explain how this fractal is constructed, how this is a fractal. Okay. Yeah, ready? I'll give 1 more minute just to see how this is being done. So these are the steps. This is the first step. This is the second, I mean, zero step, first step, second, third, fourth. And you can still continue as you wish. You can still continue. Okay. Okay. Ready? Shall we tell? Okay. So you start with a metal plate. Think of this triangle as a metal plate. Okay. I mean, take a metal and cut it in form of a triangle, right? Then what you do in the next step, you remove the middle part of the triangle, the upside down inverted triangle, right? You remove the inverted triangle part. Okay. So you will be left out with this metal plate now. Okay. The black is the metal content. The black is the metal content. Okay. So now this is not there. What you do next? Whenever you see a triangle, you remove its inverted middle part. Whenever you see a triangle next. So how many triangles you see? Three black triangles in the second step. So you remove the middle triangle from each of them. So you are left with, you can see this removal, this removal, this removal, right? Now how many triangles you are left with? 1, 2, 3, 4, 5, 6, 7, 8, 9. From those 9 triangles, you remove the middle part again, right? So you are left with this. Okay. Now the number of triangles again increased. Okay. At every step, the number of triangles is increasing, right? So from this part, you increased again, right? So like that, like that, like that, you can go on, and the structure repeats. Okay. That's how you create this self-similar fractal. Okay. And this is famously known as Sierpinski triangle. I think, yeah. I mean, I messed up a bit. Yes. Ready? Okay. Now, this is a fractal. Okay, this is a fractal. Why? Because if you zoom in this part, if you zoom in this part, this looks like this part. Okay. The more and more you zoom in, it will look like a basic part. Okay. Basic starting part. So it's a fractal. Now my question is, what is the dimension of this fractal? How we can show that it is indeed a fractal? Okay. See, line and square or a cube did not have fractional dimension. They had integer dimension. Mind you, the previous work, the line, square and all, they have integer dimensions. 1, 2 and 3. But this fractal, will it have integer dimension? That is my question. So naturally we can see, let us compute, okay. So we'll apply the same idea. What is the ideas? What is our equation? Number of small copies inside the big copy, okay, is equal to the magnification factor to the power d. where d is the dimension of that geometrical object, right? So now my question is, suppose you take this, you concentrate on these two figures, n is equal to 1 and n is equal to 2. Okay, you concentrate on these two figures only. Okay, you concentrate on these two figures, n is equal to 1 and n is equal to 2. So my question is, this is the bigger part, right? This is the bigger part, and this is the small copy of it. Okay. Now my question is, how much magnification factor you have to do to reach to the n is equal to 2 state? That is my question to you. So you can see that this small guy is present here, right? You can see a part of it, right? Now, how much you have to stretch it or magnify it so that you can cover that big part? Can you tell? Okay, I will give you an idea. Like, take suppose this side as L. Suppose this is side L. Okay. Now, how much? This is like 2L, right? This is like 2L. So you have to stretch it on this side by two times, on this side 2 times, on this side 2 times. Then only this structure can be accommodated. Okay. So if you stretch this L into 2L, suppose this is L, this is L. So you have to stretch it 2 times. You have to stretch it 2 times, right? On this side, you have to stretch it 2 times. On this side also, you have to stretch it 2 times. Okay. So the magnification factor will be 2. It won't be 4. Okay. The magnification factor will be 2 because you are magnifying on the dimensions 2 times. Okay. Only in one dimension it will be counted. So magnification factor. So what's the magnification factor here? 2. Okay. So, so the magnification factor is 2. Now, how many small copies you can fit inside this? How many small copies? Hmm? How many copies of this n is equal to 1 can you fit inside n is equal to 2? Can you see there are 3 copies? 1, 2, 3. Right? So you can fit this copy 3 times here. Hmm? Okay. Don't go with the size. Don't go with the size. If you think about the size, you will feel like I have to contract and then fit. No. Okay. The size is the same. The size is the same. But here we are trying to see what is the magnification factor, like scaling behavior. So size will be the same. Don't think this you have to change. The size will still be the same. So did you understand that you have to fit this 3 times so that it can be made, right? So this copy you can see 3 times, right? Now, okay. Now, okay. If you have not understood properly, let us go to the next one. Like maybe let us see about this big picture. Okay, this is the big one. How many of those copies you see here? Yes, 3, right? So from this step, you either go to this step or from this step, you go to this step. I mean, same number of copies you are fitting. Okay. So the formulas is not going to change and result is not going to change. Okay. So you can see that the number of small copies in big copy is 3, right? Okay. So how can you compute D? So you got 3 is equal to 2 to the power D, right? So you got 3 equals 2 to the power D. So what is D? What is D? Hmm? How will you find D? Hmm? How will you find D? Apply log on both sides, right? Apply log on both sides. So apply logarithm on both sides. What you get? If you apply here log 3, then log 2 to the power D. So what is this? Log 3 equals to this d will come to the front. That's the property of logarithm, right? So d log 2. So what is d? Log 3 by log 2. Can you find what is this? Maybe Google it. Log 3 by log 2. What is the value? Hmm? Yes. 1.585. Okay, 1.585. Right? So you can see the dimension is fractional. Fractional dimension. Fractional dimension. So you can see that for this Sierpinski triangle, the dimension is a fraction and therefore is a fractal. Okay, therefore is a fractal. So therefore this is a fractal. Sierpinski triangle is a fractal with dimension 1.585. So you might be getting this kind of question like this figure is given, compute the dimension of this fractal. Okay, what is a fractal and how you get the dimension of this fractal? Show the steps, something like that. Okay, so you can do this step, right? Shall we go to another example? Another fractal, right? Okay, let us go to this fractal. Okay, this is another fractal. Okay, this is another fractal. This is known as snowflake fractal. Snowflake fractal. Okay, this is a snowflake fractal. Now, does it look like a snowflake? Okay, I mean, it is looking like the game. I hope you have played this game in your video game, like this. You were getting a hand video game, right? Right, some around 100, 200 rupees, and one tiny. It looks like this very nice thing, and different shapes. It was coming. Okay, and there was a tiny display here, and you are having these buttons. Okay, one big button was there. Okay, in that cyan color you are getting yellow color or red color things, right? And you are pressing, and up to a point that it breaks. Okay, I hope you remember that video game. Okay, have you break that video game? Yes, I also have broken that video game to see how what is inside that makes this happen. Okay, and I found a very black color chip inside it and a circuit board. I did not understand what it is. Okay, but it looked very nice. Okay, but anyway, that's a video. Okay, so in that you were seeing this kind of structures, right? This kind of structures, isn't it? This kind, I think this kind of structures, and it was going upwards, right? It was going upwards. I hope you remember. Maybe if I do it black color, then you can remember more. Okay, so yeah, so I hope old days are getting fixed. So, okay, let us see what is the dimension of this fractal. Is it a fractal? Yes, it is a fractal because you see this, we take a point, how you construct this fractal. Let us see about construction, how we construct this fractal. So, take a point n equal to 0, how you transfer this point like this. This point becomes this. That's the idea. Okay. So, this point becomes this point, n is equal to 1 point. So, n is equal to 1, the structure you got, whatever point you take, every point will be replaced by that structure. Okay, every point will be replaced by that structure. Fine, are you getting? So what will happen to this point? So you see this point, how many points are there? I will clarify. How many points you see? 1, 2, 3, 4, 5, and each of those 5 points have transformed. This point transformed to this point transformed to this, the middle point transformed to this structure, bottom point transformed to this point, again this one. I hope how next iteration the fractal is looking, you can reconstruct. I hope it is clear. Okay, fine. From this, now you can construct this big structure. Okay, every point you have to make it like that now. So you can see, you can get a feel of the use of computation here. Okay, I mean, after a certain point, you cannot do it by hand. It is undoable by hand. Okay, you take days and days to make it, and high level of concentration is required to make this fractal. So you can do n is equal to 10,000 also. 10,000 steps, how it looks like in computer. Okay, you can code this up. You can code this fractal and make the structure. Okay, that is this snowflake fractal, right? Now, after you know how it is being constructed, can we compute the dimension of this fractal? Can we compute the dimension of this fractal? So what we should apply? How many number of small copies fit inside big copy is equal to magnification factor to the power d, right? So can you see how many number of small copies are there? Yeah. Okay. How about we concentrate on the case from n is equal to 1 to n is equal to 2? Can we construct the case from n is equal to 1 to n is equal to 2? Okay. So let me remove all these things so that it will be clear. Okay. Fine. So the idea is, if you see this diagonal line, right? Suppose this is of unit length. This diagonal line is of unit length. Now, if you transform this, how much magnification you have to do? So you can see this is the 3 times. The magnification has happened 3 times along the diagonal. Okay. If you stretch it 3 times, then you get this, right? So therefore, the magnification factor is 3, right? Now, how many small copies are you able to fit inside the big copy? So how many number of copies of this is present in this big copy? That's the question. How many? Yes. 1, 2, 3, 4, 5. Okay. Fine. So you can see how many number of small copies fit inside the big copy? 5. Right. So what's the dimension here? D. Log 5 by log 3. What is this value? 1.465. 1.465. Okay. So the dimension of this snowflake fractal is 1.465, which is again a fractional dimension. Okay. Which is again a fractional dimension. So you can see how to compute dimension of this fractal. Okay. You can see how to compute dimension of this fractal. Okay. Fine. Anyway, so this is another fractal I want you to introduce. Okay. So this is known as Koch curve. Okay, this is known as Koch curve. And I hope by seeing this fractal reminds you. Let me know where this fractal reminds you of. Does this fractal remind you of this? Does this fractal remind you of this? Doesn't remind you? No. Okay, so how we construct this fractal? That's the first question. Okay, how we construct this fractal? So you take, so this is the first step. At n is equal to 0 step, you take a line of unit length. Okay, you take a line of unit length. Then in the next step, n is equal to 1, what you do is you break this line into this format. Okay, you break this line into this format, that is, trisect the line so that every line is 1 by third. Okay, but keep these lines intact, but the middle line you construct, you add more lines, like you bent it. Okay, so you construct, so the line you see is 4 by 3, not 1. So the line segment you see is 4 by 3, not 1. Okay, I hope you can see this. This line is unit length, but this line has 4 by 3 length. Okay, so take this line, trisect it, this line, trisect it. Okay, trisect this line. This line keep fixed. So this line is fixed. Break this middle line into a bent. Break this middle line into a bent, upward bent. Okay, do the same thing for other cases. Okay, So can you see that this is the first step? Okay. Now how can you go from this step to the next step? N is equal to 2. So you have this step, right? Right? You have this step, right? Now every line you see, so you see that this line has been converted to this, right? Agree? Agree? Fine. Now let us consider the next step. Every line you see, you replace by that structure. Every line you see, you replace by that structure. How many lines you see? 1, 2, 3, 4. So this line you replace with this. This diagonal line you replace with this. This diagonal line again with this, right? This line again with this. I hope that is clear, right? I hope that is clear, right? I don't know how many steps you can go by hand. Okay. So you can see the more and more steps you go, the more and more, I mean, rough surfaces it is able to capture, right? The more and more rough surface it is able to, sorry, capture. Agree? Agree to this? So, but one amazing thing about this is in the initial steps, you can see these sharp points, right? But as you make it more and more number of iterations, as you make more and more number of iterations, you can see that it is still there, but when you zoom out, it feels like it is able to capture nice irregular structures. It is able to capture nice irregular structures, right? So this is a Koch curve. I mean, this can be used for your coastal identification. So for those who are working in geoinformatics, so what I mean geoinformatics or geology, what they usually do is they take a satellite image. They can take a satellite image of our sea areas and Himalayan regions, right? Himalayan regions where snow is there. Okay, which you see something like this. Which you see something like this. The structure is. You can see this is the dry land, but these are ice. These are ice, right? These are ice. I mean, fully frozen lands, right? Fully frozen states. Okay. Now you can see these kind of structures here, right? These kind of structures here, right? So how you can measure these structures? How you can measure these structures? Will you use this length meter? How satellites can understand this structure? How you think? If you approximate this with these kind of lines, it's a very wrong thing, right? You are approximating it by a polynomial or a smooth state, right? So you have to use a fractal geometry concept to perform it, isn't it? How? So this is an open question for you to find. How scientists measure the coastal lines? How scientists measure coastal lines? Okay, I mean, they take a Google Earth image. Using Google Earth image, you can find the image of the satellite, like the satellite captures images of this. So this is a satellite image, right? Now, how you can find the length or boundary of this coastline or this frozen line? Very interesting problem, right? Of course, you have to use fractal geometry to understand them, right? Anyway, so this is an assignment. Okay, how to compute what is the fractal dimension of the Koch curve? Okay, what is the fractal dimension of the Koch curve? But the moment you do this, a very nice idea is going on. Like I want you to see before you compute the dimension, what is the perimeter in the first step? What is the perimeter in the first step? Perimeter is 1. I mean the length is 1. What is the perimeter in the second step? N is equal to 1. What is it? Perimeter in the second step? You see the length is 1 by 3, 1 by 3, 1 by 3, 1 by 3. So it is 4 by 3. Now let us go to n equal to 2. Okay. Now what is the perimeter? Can you tell? 16 by? Are you sure? Think properly. The See this unit length, every length went to 1 by 3. Now this 1/3 length, this length again you are breaking it down. So it will be, yes, it will be 1/9. Each length will be 1/9. Now how many such broken pieces are there? 16. 16 broken pieces are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 broken pieces are there. So the perimeter is 16/9. 16/9 is nothing but 16/9 is nothing but 4/3 to the power 2. What was the perimeter before 4/3? What perimeter it became after 4/3 to the power 2? Right? Now what is the next perimeter? What is the perimeter here if you follow the pattern? 4/3 to the power 3. Right? What is the next perimeter here for this one? And this is n is equal to 3. This is n is equal to 4. So for the perimeter in n equal to 4 is 4/3 to the power 4. Right? So if you take n tends to infinity, I mean lot of steps you do again and again, like heavy number of steps, where the perimeter is going to, yes, but this is very, I mean, counterintuitive. It's very counterintuitive, right? I mean, the same, you started from a unit length. You started from a unit length, and the way you iterate your fractal again and again, the perimeter is increasing, 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 and going to infinity. But perimeter is going to infinity, but the area is finite. Is the area infinite? Is the area infinite? No. Area is not infinite. Right? Area is not infinite. But the perimeter is infinite. So perimeter is going to infinite, but area is finite. Okay. So this is the puzzle. This is the puzzle. Okay. So yeah. Okay. But the dimension is your homework. What is the fractal dimension? It is your homework. What is the fractal dimension of Koch curve? That is your assignment. Okay. Fine. Good. Anyway, so actually, I mean, it is something known as, like, let us clarify something more. That is, these are mathematical fractals. The fractals, these are mathematical fractals versus real fractals. Okay. So what are mathematical fractals? Sierpinski triangle, right? The triangle we saw first. Snowflake fractal. These are mathematical fractal. I mean, use mathematical rules to make these fractals. Koch curve, right? What are real fractals? Trees, coastlines, broccoli, anything, anything else? Lightning strikes. Okay. But the thing about mathematical fractals, the point about mathematical fractals is you can zoom in ever and ever, and it will always give you the same copy, right? But in real fractals, that you cannot zoom in forever. I mean, there is a limitation. Okay. I mean, after you zoom in further, you will start to see atoms and molecules. So in real fractals, you cannot zoom forever. Okay. Whereas in mathematical fractals, zoom forever. Okay. I mean, self-similarity is forever. Self-similarity at infinitely many scales. At infinitely many scales. That we saw a video last class. I hope you remember. The more and more it was zooming in, the more and more it was computing, and it never stops. Okay, it is your computation limit that will make it stop, else it will keep on going. Whereas for real fractals like trees and all, there is a limitation, right? I mean, you cannot zoom in forever. Cannot zoom in forever. Okay, so there is a limitation between real fractals and mathematical fractals. But mathematical fractals tell you about or gives you an intuition about the nature's fractal geometry. Okay. However, like it doesn't mimic exactly. So yeah, this is an idea. Okay. Now, how to create fractals? I mean, how to create fractals? How to create fractals? Any ideas? How to create fractals? Okay. So, how many of you have? Okay, we'll come to that later. Like how to create fractals? That's the question. How to create fractals? So you can see, like fractals can be following a rule. Okay, like I showed you a few pages before, right? Like you take what was the first fractal we decided, like this one, right? And then we removed the middle part, and we kept on removing it, and we started to seeing this pattern, right? So now my question is, let us play a game. Let us play a game. Anyone has a coin? Anyone has a coin? Let's play a game. Okay. How many have coins? This is UPI world, but we should have. You have. We play. Okay. So okay. So the idea is we'll start with a unit length. This is the unit length. N is equal to 0. Okay. The game rule is this. The game rule is this. Okay. What is the game rule? If you toss a coin, okay. If you get heads, then this fractal represents this next step. Okay. The moment you will see tail, it will be bent down. Okay. Ready with the game? Okay. So we will play this game. So this is n is equal to 1. Yeah. Tail. So this line is converted to this. Okay. Now, yeah. Next. Hmm. Head. Okay. Now it is head. Now it is head, right? Now it is head. What you will do with each line segment will be replaced by the upper bend. Each line segment will be replaced by the upper bend. So how it would look like? Yes. Yes. Agree. Agree to this figure. Shall we play next? Okay. So you got head here, right? First time you got tail, then head. Now tail. So this is tails now. So what will happen in tails? Every straight line you see, we will replace it by downward bend. Downward bend. So you will see, let me draw with this red one. Okay. So we have to be very careful. Okay. I mean, it's done. It's done. Okay. So, but anyway, I mean, I can still go on. I mean, yeah. Okay. I mean, yeah. Yes. Yeah. This is the idea. Okay. So this is that fractal. Fine. So you can see I followed the rules. Okay, nowhere it is downward, nowhere it is upward bend. But you can see how different the structure is from the structure I had shown. Okay, how different the structure is from what I had shown. So this can be a new coding challenge for you. This can be a coding challenge for you. Can you code this up? So I gave this assignment last year also. Okay, I gave this assignment last year also, and there were BioA students in this class also last time, and a BioA student made this. Okay, so I hope I will see this code from your side. So can you code this up? I mean, number of trials. Yeah, I mean, every step it will flip either tails or heads randomly, right? And you will create a fractal. You will create a fractal. So when you create a fractal, how the structure finally looks like, and n will be an input. N is equal to 100 steps, how it looks. N is equal to 200 steps, how it looks like. N is equal to 1000 steps, how it look like. Okay. And is there a pattern? I mean, when you see n is equal to 200 step, n is equal to 300, n is equal to 1000. 10,000 are you seeing any patterns even though it is random? That is the question. That is the question. Okay. So this is a way to, this is something known as random fractals. This is known as random fractals. So fractals that are created randomly. Okay, fractals that are created randomly. Okay, fine. So same thing you can play with the Koch curve. I mean, this is known as quadratic Koch curve. I mean, what do we do in Koch curve? Anyone? We take this line, break it into this, right? Now people started asking, why we have to break into this? We can also break it into this. Okay. So this is known as quadratic Koch curve. Okay. I suggest you type it in Google and see the image right now. Okay. Quadratic Koch curve. See Google images, how it looks like. Okay. Fine. Right. Can any one of you show me the laptop like this, big screen, and I can see? Okay. Can you show someone? Yes, exactly. See the computer over there. So does it remind you of anything? I hope it reminds you of a snake game played in your Nokia mobiles. The more and more it eats, the more bigger it gets. Okay. So I hope you remember the snake game in Nokia phones, right? Okay. So now we see what are the other ways to create fractals. One is iterated function systems. Iterated function systems. Okay, IFS. Iterated function systems. Okay. So what happens to this? I mean, why only a line? If you just do a line, you cannot cover all the objects. What about box? Okay, what about a box? I mean, if you have a box like this instead of a line, you can do the same thing to this box. And this, how this box will look like? Anyone? How this box will look like? Isn't it? The box looks like this. You break the box into, tricep the box, make, don't make any changes to the left and right side of the box, but the middle part of the box you make it bent upwards. Okay. So if you keep on doing this to areas, these are area now, it has area now. This has an area. If you do this with areaed objects, like with area not equal to 0, then you will start seeing this in real life objects. Okay. Fine. Another is known as, we will not go much into deep into this. Another is L systems. L systems. Okay, L systems. This is known as, I will tell you the real name in the next slide. Okay. It has a name. Okay. So this is an algorithmic way to create a fractal, like axiomatic way. This is an axiomatic way to create fractals. Axiomatic way to create fractals. What you do is something like a production rule. It is like a production rule, right? So what you say is n is equal to 0. Suppose you are here, then for n is equal to 1, you are bent into this. You have this object. You have this object right now. So how you got this object? Okay. So you will tell that yes, you go forward. Okay, you go forward. Then a plus. Plus means it is like bent left 60 degree, right? Bent left 60 degree. That means you make 60 degree to this line, right? Then you say again bent forward. Okay, make it another 60 degree towards the left, another 60 degree towards the left. So it is bent down, and again F. So move forward, right? So if you give this code to the computer, you feed this code to the computer, it will make this figure to you. Okay. So you can learn more on this L systems. Okay, you can learn more on this L systems. I will not go into detail. So this string of letters, the string that is F plus minus, this string of letter decides the shape of the fractal. And this string continues to increase in size as the number of steps increases. Of course, your length increases, so the more number of operations you have to tell the computer to do. So you have to find an algorithmic way to code this up, right? I mean, it has a pattern. It has a pattern that it will repeat. You don't have to write this manually. Okay, you will put it in a for loop and it will keep on iterating it again and again and again, making that geometry. So to do this fractal geometry in your coding part, you don't need much ideas. You just need a for loop. Just need a for loop. You keep on iterating using a for loop. Okay. Now let us see into something new, that is diffusion limited aggression. Okay. This is a natural way to create fractals. Okay. So you can see this is known as a DLA, diffusion limited aggregation. So you can see this DLA, this is I have taken from Wikipedia. You can see DLA consisting of about 33,000 particles obtained by allowing random walkers to adhere to a seed at the center. Okay, different colors indicate different arrival time of the random walkers. Now, what is this? I mean, this is very abstract, right? This is very abstract. Now, let me give you a real-time example. Okay, real-time example. Take what you call your what do you call plates. Take a small plate you have where you have ice cream. Take a small plate where you have ice cream, right? So take that metal container, pour some water, right? And keep it in your house or outside. Outside. What will happen after some time? After you leave it outside for many hours? If you leave for some hours, it won't dry. If you leave it for 1 2 days, it will dry, right? I mean, just 3 hours, it won't dry. So what you see, this is the particle length, right? And this is water here. This is water. Maybe what we can do is draw water here. Okay. So this is water. Okay. So now the idea is, if you have this water, what happens to this? Now the dust particles started to stick on the water surface. Am I right? I hope you have seen this. I hope everyone has seen their bucket of water, the surface of the bucket of water before doing anything with it. Okay. I hope you have seen the surface of the bucket, right? What you see, the dust particle come from the top like this and get stuck in the surface of the water. So let us draw that in maybe which color we will use? This one, okay? There is a tiny dot here, like this, like this, like this. So they keep on aggregating, right? They keep on aggregating. The more you allow them to be, it keeps on aggregating on the surface of the water, and they don't aggregate like we don't know yet whether it is randomly they are aggregating or in what rule they follow, not yet uncovered. But they make this kind of structure. Right? How many of you have seen fungus growth? Fungus growth on trees, maybe on trees. No? Fungus growth on food. Okay, have you seen they have a pattern? I mean, when you see carefully, there are tiny, tiny particles like they follow this kind of structure. They look like this. They looks like this. Okay. Sometimes. I mean, if you have not seen, go back home, try to find an area where you have fungus. Okay, and see. Okay. Fine. Okay, another area is grapes. How many of you have eaten grapes? Yes, grapes. So when you eat all the grapes, what you are left with? That structure, right? That branching structure. So this assignment also I gave last year, that buy grapes, eat grapes, and bring to the class the remaining one. Okay. So when you bring the remaining one, it will look like this mostly. See the branching structure of the grapes. It is very complicated. It is not simple. Is the branching structure of grape very simple? So, I mean, you might not have understood or looked into from that angle. So now I suggest this week buy one that grapes, okay, one kg of grapes, and start eating the grapes, okay, and keep the skeleton inside, and then watch the skeleton. Then watch the skeleton. Okay, take a photo of it, print it out, okay, and show to other people what it is. So they will be confused what it is. So you tell, yeah, it is a fact. Yes. So that's something nice. Anyway, so that is one idea. Okay, let us just go through one part before we have a break. Okay, just one part. Okay, before we have a break. That is another way to calculate fractals. That is another way to calculate fractal. That is known as the box counting dimension. Box counting dimension. Okay, how to use box counting dimension to find out fractals. That means we will play with boxes. We will play with boxes. Okay. First of all, why we need dimension? Why we need dimension for at first? That is the question. I mean, why we are talking about length has dimension 1, area has dimension 2, sphere has dimension 3, cube has dimension 3, this has fractal dimension. Why? Even though we have length and area, why we concentrate on fractals? Even if we have length, area, volume, why we concentrate about dimensions? We concentrate about dimensions because we saw that there can be geometric objects which can have a finite dimension, but their length is going to infinity and area is not going to infinity, right? Did we see that kind of geometric figure, right? Yes, Jaco is saying yes. Good. That means you are attentive. Yeah. So what does it mean? We saw the Koch curve. We saw the Koch curve, right? We saw the Koch curve. Where we saw that? Where? Here means. Yeah. Come, draw. Want to draw Koch curve? Want to draw? Okay. Anyway, we'll see. So length and area, length can go to infinity. We can see, we saw that length goes to infinity, area can go to 0, but dimension never messes up. Dimension is a quantity which never messes things. Okay. So therefore, dimension is another metric which can give us an idea about the geometric figure. Okay. So therefore we look into dimensions, even though we have length, area and volume. Even though we have length, area and volume as a metric, we've tried to find another metric which can give us more information and more efficient than the length, area and volume. That is the dimension. If your dimension is 3, you can clearly say that it has a volume. If your dimension is 2, you can clearly say it has a length and area, right? If you have a line, you can clearly say the volume is 0, area is 0, length can be finite or infinite, but it has dimension 1, right? So dimension is a good metric when it comes to identifying geometric figures, right? Okay, let us do experiment again. We start with line. Like we started before in the method, we start with line again, right? So let us consider this unit line segment. This is a unit line segment. Now I am taking a box of side 1 by 4. I am taking a box of side 1 by 4. Now I am asking you how many boxes you need to fit inside this line so as to cover this line, right? So as to cover this line. How you will fit? Yes, I can fit one box here, right? I mean, I have to make the box a bit bigger. You can, yes, one box, second box, third box, fourth box. Increase the line. Okay. Fourth box, right? So 4 boxes you are fitting, right? So can we say this? Let us make a table, side of the box, side of box, and number of boxes needed to fit, need to cover. Okay. So inside of box we denote it by S. That is the side of the box. Normally notation is S. Number of boxes needed to cover that shape is N of S. Right? Fine. So what is the side of the box? Here 1 by 4. How many boxes you took to cover it? 4. Suppose you take a box of length 1 by 8. So how many boxes you need to fit this one unit length? 8 boxes. So if the length is 1 by 8, number of boxes you will take is 8, right? Okay. Suppose you take 1 by 16th the length. So how many boxes? 16, right? Fine. Now let us do another experiment, okay? Maybe we can take, yeah. Can we increase the size of this length? That is another experiment, okay? How about we increase the length size to 2? Suppose we increase the length size to 2. So what you get here? Suppose the size of the box is 1 by 4. So how many boxes you need? 8. For 1 by 8? For 1 by 16? Yes, okay. Fine, good. Okay. I mean, after this, what? I'm waiting. Our objective is to compute dimension. Can you see how dimension is happening between these two quantities? How we can find dimension? But you see that when I increase that length, the denominator. Some might think that denominator, whatever I'm seeing, it is here, right? 1 by 4, then 4. 1 by 8, then 8. But suddenly, when I increase the length to 2, I took 1 by 4, it turned to 8, not 4, right? So let us take 4. Let us take the unit to be 4. So if you took 4, if the size is 1 by 4, what should be the length? 16. If you took 1 by 8, 1 by 16. So can you see something is happening here? Can you see something is happening here? And what is happening here? So from this quantity, you can write from this data. From this data, you can establish a relation. You can establish a relation that is n of s is equal to some constant c times 1 over s, the side of the box, to the power dimension. Okay. So see that when your dimension is 1, if you put d equal to 1, c equal to 1, if you put d equals to 1, c equal to 1, then n of s is just 1 by s, which is exactly following this case, right? Which is exactly following this case. Now can we take something else? Can we take something else? Do you want to do with a square? If you take a square, how this will change? That is my question. You took a length. You took a length and then understood this. If you take a square, then how this will change? No. What I'm asking is quite simple. You take the small unit square of 1 by 4 length and then you take a square of side 1. So how many boxes, small boxes, can you fit inside? How many boxes? Hmm. Hmm. 16 boxes. So S is 16, N of S, sorry, S is 1 by 4, N of S is 16. N of S is 16. So what, if you apply this rule, what is, if suppose C is equal to 1, what you get? N of S is 16 is equal to 1 times 1 by 4 to the power D. What is D? What is D? I mean, I don't understand where, I mean, you're not even telling any mistake to me. What is this? S is equal to 1 by 4. How come I can write 1 by 4? It is 1 by 1 by 4. You put this in eyes. Okay. Anyway. Okay, let us watch a video, very nice video where he explains using a oil paper, he is explaining how to use box counting dimension to compute fractals. Okay, now you understood the box counting dimension, right? Now he will use this box counting dimension to show you fractal. Okay. Mm, I mean, so this is a very nice website like Complexity Explorer. It is from Santa Fe Institute, okay, in USA, and they usually give free open courses to understand nonlinear dynamics and complexity. Okay, so there is always a complexity in everywhere you go. Like you see the traffic congestion. Okay, it has a complexity. The people walking in a bridge, the people gathering a high quality event, or like music concert. Okay, people gathering in that, there is always a complexity involved. How to understand the complexity? So this is Complexity Explorer, and he will explore you what is a fractal, okay, and also how to compute using box counting dimension for Sierpinski triangle. Okay, he has a book into its name in nonlinear dynamics. So we'll see. To the previous video by suggesting the following relationship between NS and S. N of S is the number of boxes of side S we covers an object. And that will be given by this expression D. C is the constant. 1 S. T is the function. So let's box counting for this triangle. Calculate this dimension. And we'll compare that to the self-similarity. So here is Sierpinski triangle. And I've made this a right triangle now. These are boxes in this one. So let's see. Here we go. Line this up. Just like so. I can now count boxes. So side here is a quarter. Let's see what we have. 1, 2, 3, 4, 5, 6, 7. I hope you understood why S is equal to 1 by 4. Right? Understood, right? The single unit is this triangle over here. That is, each has 1 by 4 length. And that you can put 1 by 4 times if you want to cover the full Sierpinski triangle. So S is equal to 1 by 4 of that box. Okay, the unit box. And he counted how many such boxes can fit inside the Sierpinski triangle. There are boxes which are empty. There are boxes like this box is empty. So he did not count that box. This box is empty, so he did not count that box. So you can see how many boxes he counted. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This one, the shape is in this box, so I can completely cover the shape. So let's keep trying. These 9 boxes. Now let's go down a side. What if we have a side in E? There we go, that side's going to be. So now the size is decreased, so the boxes are even closer. So let's see. Cover the shape. That would be 1, 2, 3, 6, 7, 8, 9 boxes. I don't need this one. The Sierpinski triangle is in there. And I don't need another 9. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Seven. Let's do one more test. Side 16. Out of me. See what we're gonna get. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. That's just for that. So 9 boxes there. But then there are 1, 2, 3, 4, 5, 6, 7 of those boxes. So the answer then, the total is going to be 9 times 9. So that's the data. Those are the numbers we get. Approximately. Here's the data from side S boxes. So what we want to do is think about plugging these values into this equation. And our goal is D. We want to figure out the dimension. We saw in this previous example that this constant C was 1. First two examples we had those things. So I'm just going to guess that C will put it down. I'm interested in this. Later on, in the next subunit or even the one after that, I'll talk about a more systematic way of dealing with both C and D at the same time. But let's assume that C equals 1. That's not always a good assumption, but that's not what we're going to in this case. So then we want S. So let's plug in and use S. Is a quarter, so that 1 over a quarter. 1 over a quarter is the same thing as 4.
I mean, this is very trivial calculation. So you can see similar kind of equation we are getting. I mean, previously also, now also.
Okay, so this is the box counting dimension for the circle C triangle. We come up with a numerical value using a calculator. 1.585.
So you see, previously also we got 1.585. So it matches. Both the method are working.
This is the same number we got. Self-similarity dimension for this triangle. Let's review how we did that. Not really great. So the self-similarity dimension is given by D in this equation. The number of small copies in a large object is equal to the magnification factor raised to the power where D is in the dimension.
This I already covered.
Triangle. We have 1, 2, 3 small copies. And the magnification factor is 2 to take this length, stretching out 2 the small copy of this big. And the quadrant is all E.
So you can see there, these are the two methods. I mean, self-similarity dimension and box counting dimension. Anyway, so now you see that how these are like, related to each other. Okay. So I hope you can go through this complexity explorer and learn more about this complexity science. Okay. So They are very cool videos, and they present it in a very nice way. Actually, I started learning nonlinear dynamics by Complexity Explorer, because as a master student, they make it free for students. So I obtained a lot of certification courses on this also. So what you can do with this? Okay, what you can do with this? I mean, uh, you can consider this example over here. Can you tell me the formula we have written down? N of s is equal to, yes, c times 1 by s to the power d. So if you have data, if suppose you have only data, right, you can convert it to a regression kind of problem. Okay, how? Take log on both sides. If you take log on both sides, log n of s is log c plus d, sorry, minus d log s, right? I hope that is clear. Or did I make any mistake? Okay. Now, if you have some data points, that means, let me say you have S1, S2, and correspondingly N1, N2 data points. So how we will get log N1 is equal to log C, okay, log C minus D log S1. Similarly, log N2 is equal to log C minus D log S2, right? So you can play around and compute the dimension D if you have data points. If you have data points, this you know, this you know, this you know, this you know. So you can always compute D for them, okay, from each points. So you can say that you can compute D is equal to log N1, log N1 minus log N2 divided by, anyone? What should we get? Yes, think about it. But you will get something like this: minus times log S1 plus log S2. You can write it in a better way. I'm leaving it to you. Okay, how to do this? If you have a set of data points, how you can compute, and what it gives us, you can see that if you plot it, and compute the slope will be the dimension. Okay, if you compute the straight line, it is a straight line equation. You can see this quantity as y2 minus y1 by x2 minus x1. You can think of this quantity as y2 minus y1 by x2 minus x1. Given 2 points x1 y1, x2 y2, what is the slope? 2-point formula, right? Slope 2-point formula, y2 minus y1 by x2 minus x1. So what you can do actually, like from this equation, you can think of a straight line equation as a straight line equation, right? This is a straight line equation. Just like, I can write log n of s is equals to, say, minus d log s plus log c, right? So this can be y, this can be mx, this can be c, right? This can be y, this can be mx, this can be c. So y equals to mx plus c. So when you draw the line, it will be something like this, right? Where this is that quantity c. This is the quantity big C, that is log c, right? And what is the slope here? Can anyone tell? This is log ns. The y-axis is log n of s. The x-axis is log s minus log x. So this quantity is nothing but d. That is the slope. Slope is equal to d. Slope equals to d. Okay. Did you understand what I wanted to communicate to you? No. Shall I explain it again? Okay. So let me use some highlighters. So we had this equation, right? We had this equation. From this equation, I applied log and I got this equation. Agree? I got this equation. Now, can you look this equation as a line equation of the form y equals to mx plus c? If you see this as a line equation, what you get? Log n of s is equal to minus d log s plus log c, right? So what you can do is, this is y. Think of this as y, right? This as mx and this is c. Can you think it of as a line now? Y equals to mx plus c. What does y equal to mx plus c represent? A straight line with intercept c. What is intercept? The distance between y-axis, right? This is the c, right? And what is the slope here? Slope of this straight line? That is d. So this is log ns, y-axis, x-axis is minus log s. So this is only d is remaining as slope. So the slope m equals to d. Slope equals to m equals to d. So if you have certain data points, you can always use those data points to compute the dimension. Okay, that is my another visualization of how to look this equation actually, right? So how you can think of it as a, I mean, regression curve and compute the dimension also you can analyze this. Okay. Anyway, so I think this is done. So